So, this is my first time with the Google version of slideshow. Okay. Nothing on this first slide looks like you have to write down on your little note sheet. But let's give you a little bit of background information. The last few class periods, I've really tried to emphasize this idea of stability and the octet rule. We're familiar with this? Now, elements don't walk around thinking to themselves, golly gee, I wish I could lose those last 3 electrons to become more stable. Or man, wouldn't it be swell if I could gain 2 electrons to become more stable? That's not how it works. Atoms don't have thoughts or feelings or wants. And yet they are able to either lose electrons or gain electrons in order to achieve stability. What we have to go over today then, and we'll continue this with the lab that you're doing and then into next class period, is what mechanism do they do in order to achieve stability? And that's what we refer to as the trends of the periodic table. Certain things will determine that some elements are good at gaining electrons. Some elements are good at losing electrons to achieve that octet. But what we want to get away from a little bit here today is what I would call personification. Again, these are not individual things that have thoughts or feelings or desires. Instead, there's a tendency for some things to gain electrons. There's a tendency for some things to lose electrons. That's what we need to go over. Now, it is our belief in chemistry as a whole, if we can understand the size of an atom, we can understand the other aspects of this. So let's start off with atomic radius. On the top of your sheet, what is atomic radius? I mean, it's half the distance between 2 bonded atoms, like I have a picture shown here. Really, when we say atomic radius, we're referring to the size of the atom. And I'd almost be okay if you jotted that down instead for your kind of definition. Because if something has a small radius, I mean, this is just like a circle, radius, middle to the outside. Something with a small radius has a small size. Something with a large radius has a large size. So really, the atomic radius is the distance from the nucleus to the valence electrons. And we use this to show the size of the atom. And not that we'd ever assess this for you. However, today's lab activity, you're going to be looking up measurements for radius. Just to let you know, those measurements are in a unit called picometers. You did in metric unit 1, nanometers. That was last unit. 10 to the 9th nanometers is 1 meter. We're actually going to cover what nanometers are in conversions in about a week's time. A picometer is 1,000 times smaller than a nanometer. We need 10 to the 12 picometers to equal 1 meter. But again, atoms are super duper tiny. So we need a super duper tiny unit of measure in order to measure it. So again, for atomic radius, it's the distance from the nucleus to the outer electrons. I just refer to it as the size of the atom. Are we okay with this first slide? Okay. Not all elements are the exact same size. Some are bigger and some are smaller. And there are 2 factors that help determine that. Those 2 factors I have in bold on the top of the slide, which happens to be things that I'm asking you to write down as well on your note sheet. So I'm going to start with the nuclear charge. It's how many protons you have in your nucleus. Again, feel free to summarize. Positive protons in the nucleus attract the negative electrons in an atom. Feel free to abbreviate protons as just a P with a plus sign. The nuclear charge is referring to the number of protons in the nucleus. In other words, if one element has a larger nuclear charge than another, that means it has more protons. And why that's important is if the size of the atom is positive nucleus and negative electrons, the more positive in the middle can attract the negatives, draw them closer, make the atom smaller. So we need to think about that as we're doing our lab today of which elements have more or less protons. Because that can help us determine which things are bigger versus smaller. The second term, which is a little more complicated, is called electron shielding. Electron shielding is stating that core electrons. I introduced this term to you once a couple of class periods ago, but I don't know if many people picked up on it. Core electrons are inside electrons. They will lessen the attraction of outer electrons to the nucleus. Now, because this shielding topic is a little more complicated, there's a box on your note sheet that says Bohr model of argon. Bless you. I'd like to draw that out for you right now so you can see that Bohr model of argon, and then we can relate this idea of shielding a little bit better. Okay? So I'm going to switch over to the Smart Notebook here for a minute. Bohr model should start with a nucleus. And if it's argon, it has 18 protons. The mass of your isotope on your note sheet is 40. 40 minus 18 is 22. The first shell of electrons for boron has 2 in it, just like every element. Again, there's 2 across. Second shell should have 8. Third shell has 8. Now, I did colors specifically for this. That outermost ring, that's your valence, your outer electrons. My 2 rings in blue, those are the inner electrons, or called the core electrons. What the core electrons do is they block some of that attraction between the positive protons and the outer shell. Think about it. If you only had 1 core shell, there'd be less blocking. If there was 5 core shells, there'd be more blocking or more shielding. The size of the atom is based upon 2 things. How many protons are in your nucleus, nuclear charge to attract and pull things in, and how many shells of electrons you have. Because the more shells you have, the less the attraction the nucleus has for the outermost shell. It makes it hard to pull it in. The reason why we emphasize this is because if you can understand the size of the atom, you have a better chance of understanding why some elements will gain electrons and some elements will lose electrons. The first trend then after atomic radius that we have to go over is ionization energy. My first bullet point here is the definition of ionization energy, if you want to jot that down in your note sheet here. Ionization energy, we often abbreviate IE. That's what you see on your sheet there, just to make it left to right. Ionization energy is referring to the energy needed to remove an electron. The first ionization energy would be to remove the outermost electron. And that's what we're going to be studying. There is actually a second ionization energy, a third, a fourth. Heck, we can tell you how much energy is required to remove every single electron from an element. We focus on the first ionization energy. We kind of just use that term with ionization energy interchangeably. So, losing the outermost electron. Elements with low ionization values will lose their electrons easily. So when you see on your note sheet high ionization energy, if there's something with a high value for ionization energy, that means it takes a lot of energy to pull it away. That would be hard for it to react. On the other hand, just like I've written here, low ionization energy easily loses electrons. That means it's reactive. Gaining or losing your electrons is causing a change, causing a reaction. And again, it is a measurement that you're going to be writing down a little bit, so I tell you the units as a kilojoules per mole. So in a little bit, when you're doing the lab activity, you're going to see values for ionization energy. Some are bigger than others. The smaller the value, the easier it is to lose electrons. And that's not a bad thing, because remember, some things lose electrons to achieve stability. It's the expression taking candy from a baby. Why is it easy to take candy from a baby? Babies are not strong. I know, I have one 2-year-old, and she's going to collect a lot of candy tonight, and I'm going to take all of it from her. On the other hand, you don't hear the expression taking candy from Vin Diesel very often. Vin Diesel is a large man. If you try to take anything from him, you're going down. It would take a lot of energy to do that. So when we look at ionization energy, it might even be helpful for you in your note sheet to circle where it says low IE. Because if you have a low ionization energy, it means it's easy to lose electrons. And gaining or losing electrons can get you to being stable. So when we talk about loss of electrons, we're talking about ionization energy. Last slide of notes, then I have to go over the bottom part a little bit with you. Electronegativity. If ionization energy is about losing electrons, electronegativity is about attracting or gaining electrons. And notice on your note sheet again, it has a high EN and a low EN. A high electronegativity means you're good at gaining electrons. A low electronegativity means you're not good at gaining electrons. What's weird about electronegativity, though, it's a unitless value. It's just a ranking system, more or less. But it's an important ranking system that we are going to refer to in the next unit as well when we discuss bonding. So again, electronegativity, maybe circle high EN on your note sheet. Okay, so electronegativity, gaining electrons, ionization energy, losing electrons. The very last thing on this note sheet is showing you what you're going to be doing in the lab here in a minute. Again, this is not a traditional lab, this is a computer-based lab. You're going to have to look up values for different either rows or columns on the periodic table. And once you do that, you're then going to graph them. So for example, if I looked up the noble gases for atomic radius, the size of the atom, I would notice that helium is 31 picometers. I could then write down helium on my x-axis and go up to 31. What's that? 1, 2, 3. And make my little bar graph. Then I could do neon, same thing, over and over again. Those values can be found on this link that I have right here on your note sheet. Or, I'm sorry, on my notes right here. Otherwise, that link is also going to be on your lab itself. So I'm not going to go through doing this entire graph because hopefully then you'd realize, okay, neon would be next. Let's graph neon. Then argon would be next. We are going to be collecting data today in the data table, and then we're going to be graphing it. And that's kind of the evidence when we kind of talk about claim evidence reasoning within labs. Your evidence is going to be a lot of graphic data today. And then from there, you're going to be able to take it to that next step and analyze it.